Hey everyone, it's Andrew Couch here. I'm on spring break right now. However, due to the coronavirus, my spring break plans are actually canceled. But luckily, Tidy Tuesday is not canceled. And this week, we're actually looking at a great data set today. So for this week, the data set is The Office. And it actually comes with two data sets. One called Office Ratings, which basically contains the episode and their IMDb ratings and total votes, which really isn't that interesting. However, what's really cool is that it comes with a package called the Shroot package, which contains basically all the episodes and its dialogue. And what's even better about this data set is it comes with a dialogue with labels, specifically character labels. So we have each character's dialogue for each episode. So what we can do right now, and it's what I'm planning on doing, is doing some type of NLP or text mining project on this. And really the main work that goes into NLP and text mining is actually labeling and getting these labeled data of text data. So since we already have labeled data, 80% of the work is done for us. So we can kind of jump in and do some fun stuff. So I'm going to open up our markdown. I'm going to first call this TidyTuesday office. Oops. Office. Okay. And like all TidyTuesday things, we're going to load in the tidyverse. And then we're going to load in the Shroot package. Okay. And then we're going to say, we're just going to give the office data or the main dialogue data to a data frame called DF. So right now it's loading for some reason. We'll lower my webcam. Okay. So we're going to give it to DF. And now we're going to look at our actual data frame and see what's going on. So our data frame contains an index, which is kind of like a row index, which we don't really need. A season, episode name, where episode name and episode are basically the same thing. Director, writer, character, text, and text with direction. I'm kind of curious on what text and text with direction are, but first let's kind of look at it in a simple kind of table view. So we'll do df head. And now what I'm noticing right here is notice how season, episode, and episode name, I guess these first, four fields are repeated. However, character is making this unique, right? So what I'm seeing here, let's go to the next column. Okay, yep, right on. So each observation is literally the character's dialogue for that scene, I think this is literally the first thing that's said in The Office, episode 1, season 1. So that's pretty cool because it's like almost the entire conversation for each character. So it's not just the character's text, but character's dialogue for that scene. So we could actually kind of do like maybe a time series if we really wanted to, using an index, so we could see like, oh, Michael's sentiment throughout the season. But let's not get ahead of ourselves and let's start kind of looking at some basic summary statistics. So first we should see let's just count how many characters there are. So I'm going to do select season, episode, and then character. Okay. And we're going to do the unique function, because notice how these characters are duplicating. But if we do season, episode, and character, and we find the unique character, unique values for this, we're basically going to delete all duplicates. And then if we count character, we're essentially counting how many times a character has shown up in each for an episode. So it's saying how many episodes is a character in. We'll also apply this secondary command, which is sort equals true, just to sort the count. And we can see that, okay, Dwight was in 186 episodes, which makes sense because he's the main character. Jim, Pam, Kevin. Yeah, those are all the main characters. And one thing that I want to kind of do first is, if we're going to analyze some characters, we don't want to analyze 773 characters. We want to analyze, I guess, the main characters. So I'm going to do a basic summary statistics first. just to see, let's see how many the distribution of episode appearances. So our distribution is basically third quartile says there's one, which means that most people, most characters only appear once. If more than once, then the character is probably I guess a show regular, right? Because we can see how the mean is 5.818 and the median is 1. So it's heavily skewed. And we can visualize that too. So let's do a visualization of it. Oops. Okay. And then we'll just do a ggplot. Yes. X. We'll just do y equals n. Geom box plot. And I bet we'll need to do some transformations. Right, so we're definitely gonna need to do a transformation. So we'll do a scale y log 10. We'll do a log 10 transformation. And what do we see here? We see most of it is at 1. However, most of our outliers are all the way over here. So what we're gonna do also is we're gonna just filter n is greater than 1. So we're gonna just filter out characters who have only appeared in one episode. So they have to appear in more than one. And there we go. So most of our characters between Q1 and Q3 for observations are around 2 to 8, right? 2 to 8. Cool. So we don't really need to worry about that. What I'm going to do is I'm going to select count sort boop. And now we're gonna try to decide what characters we want to just analyze for our dialogue. And I'm actually gonna use some domain knowledge for this because I've watched The Office a decent amount of times on Netflix, and I know that these first 10 characters are the main characters, and I believe that their dialogue is very valuable for an analysis. So we're gonna go to 11 through 20, and again, all these characters make sense for the episode appearances. So we're gonna keep these. Nellie, I'm not too sure about keeping, but we're just gonna keep her. And then we're gonna go to 21 through 30. And right here from 21 to 30, we can see that it gets a little hazy where all these characters I would say are not as important. Although I do like Pete as a character, we're just gonna ignore it. So we're gonna select character, and to select basically the first 20 characters, I'm going to use a slice function and do slice 1 through 20, which will basically pick the rows 1 through 20. And we'll call this characters. Characters. Cool. Okay. So now we finally have an important characters that we want to use. But we also want to let's look at the writers first. So I'm going to select season, episode, writer, unique, and then I'll do count writer, and let's say sort equals true. Okay, cool. So our top 3 writers who wrote the most episodes are Mindy Kaling, BJ Novak, and Paul Lieberstein, which is pretty cool because those are also characters on The Office. They're both actors and writers. Okay, but one thing I'm also noticing is that right here, this is like a multi-valued attribute where they had multiple writers writing for that episode. So I'm kind of curious, like what writer duos, like what are the most frequent writer pairings in The Office? So what I'm going to do is I'm going to do a filter, and we'll say SCR detect writer. And so we know our multi-valued attributes are delimited by a semicolon. We can say filter all. We're basically trying to filter any writers that contain these semicolons. So we're going to do that. And there we go. We have our pairings. And we can see the majority of the writers, or the most popular duo, is Gene and Lee. However, we're also running into problems where Lee and Gene are counted as separate people. but that's fine. We know it's like about 13 of the episodes were written by this duo. That's pretty cool. So I'm gonna just comment Gene and Lee wrote as a duo, wrote a lot of episodes together. Okay, cool. So we kind of did a preliminary analysis. Now let's actually kind of get into some text mining. So I'm going to actually load up the TidyText package, which is a text mining package that really follows the tidyverse fundamentals. So now we're going to do something where we're going to use the unnest tokens function, and we'll use the output as word, and our input is text. And what this is saying is we're going to remove all of the dialogue and convert it to just words. Okay. See, all right, Jim, your queries look very fun. So it basically converts it to one single value. You know, if you consider sentences as a collection of words, it's basically a multi-valued attribute. So now we're resolving this multi-valued attribute constraint and change it to single value attributes per observation or per row. Cool. So I'm going to say, I'm going to call this a word DF. So we don't have to go through anything. Actually, you know what? I'm going to do something a little bit different. And I'm going to do unnest token, but I'm also going to do count. No, I'm going to do it. I'm just going to make a word DF. We don't have to do anything. This is to make it basically a little bit more flexible for our analysis. So we created our word DF. And now what we can do is count character and by word. Cool. So what I'm saying right now is for every character, we're going to count the words and the word frequencies. However, what we also need to do is do a inner join with our characters to filter out the relevant characters we want to analyze. So now it's only choosing characters that were inside our characters data frame. Great. So we're just going to do a group by character top top n equals 5. So we're finding the top 5 words for each character. Okay, and then we're just gonna ggplot it out. So x equals word, y equals n, fill equals character, com plus chord flip plus facet wrap. Because we are doing basically, we're making a column chart showing the top 5 words, and we're making multiple charts for each character. And we're flipping the axis because it's easier to read for the corresponding words. So we're going to do that. Okay. So you can see how it's not very great because all we see is U to the IA as the most frequent words for all the characters. And there's a problem with counting just words and not doing any type of filtering, because these words that we're seeing right now are called stop words. What's great though is that TidyText actually contains a way to remove stop words by using the anti-join, and we'll say stop words, right? Okay, and what we're using anti-join is we're just saying that if these words, if you share these values in the stop words list, we'll just remove it. So it's a really quick way to remove or filter out words that you don't want. Cool. So now we have this. If you notice that these things aren't really ordered correctly, we'd rather order it by like descending order. Luckily, TidyText actually has another way to order it very easily. So we'll use the reorder within word and character, right? And then we'll do a plus scale x reordered. Okay, and now we'll run that, and I'm going to just do some basic code cleanup. Okay. So now we're going to try to analyze top 5 words for each character, removing stop words. Cool. I'm actually going to make this a little bit bigger. So dot height equals 15, fig dot width equals, equals 15. Sweet. Okay, sweet. We're just gonna go kind of one by one. We can see that Andy, his still most frequent word removing stop words is yeah. Now you could say that yeah is a stop word, and you just add it to it if we really want to. But I'm just gonna keep it. I'm not gonna do any micro adjustments. I'm just gonna let TidyText and just do the out of the box analysis on it. Okay, so we can see that yeah and Michael are very popular words. Yeah, Jim, God, Ryan, Michael, Dwight. Okay, so one trick with this is we can actually use term frequency by inverse document frequency. Um, First, I'm going to say top 5 words with stop word removal. What we're really trying to look for is not the most frequent words that are said by the characters, but what are the most distinguishable words for each character. And that's where TF-IDF really stands out. So actually, I can just kind of add this bad boy on, right? Okay. And we're going to use TF-IDF, which is called term frequency by inverse document frequency. And what this finds is basically, it basically balances how frequent a word is and how rare a word is within groups. And within groups is basically within the characters. So we're trying to find a word that is used most by, we're trying to find a word that is used a lot by one character and one character only. So we're going to do the bind TF-IDF. We'll say word. Our document is character, and our n is n. Boom. Okay. And we're going to do a group by character, top n, TF-IDF, n equals 5, ungroup, and I'm just going to copy this thing right here because I don't really feel like typing this all over again. You could make this in a function. However, it gets a little weird. It gets a little fuzzy when you're using ggplots and functions. So I'm just going to kind of just copy and paste it in. However, you could create your own function where you can specify your n. What's going on here? Top n TF-IDF. Ooh, spelled. There we go. And I already know I have to change this fig height, so I'm just gonna fig dot height equals 15, fig dot width equals 15. Okay. Okay, well, let's see what it's gonna output. There we go. So now we can see, and here, right here, we're seeing something that's really interesting. Tuna is Andy's most distinguishable word because he says tuna the most. I don't think a single character besides Andy says tuna. Okay. Creed Brand, no one says Creed Brand besides Creed Brand, right? Dwight always says his last name. He also says Sensei. Let's see what else is kind of interesting. Aaron, Pens, Lice, pretty interesting. So right here, Gabe has Pedas. So that might be an error with our tokenization, but we don't really have to worry about that right now. But his second most distinguishable word is Chow, which is definitely a very an iconic word for him. Cool. And then Ryan, it's Wolf, Thailand, Pesto, Drake, Silicon. Let's see here. Michael, it's Jan, Holly, Packer. Oscar, it's Senator. Very interesting. Pam, her most distinguishable word is Cece because that's her daughter, Jim and Pam's daughter. Cool. So now we can see that the difference between top 5 TF-IDF words and top 5 most frequent words is just night and day, right? TF-IDF within groupings just is the superior method for analyzing um, tokens, especially when you're trying to find things that distinguish each grouping. Okay. So what else do we want to do? I'm thinking that we should do a sentiment analysis by a time series. That'd be pretty cool. So we're going to do that. Okay. So we're going to do our word DF first. Okay. And with our word DF, we're going to do we're going to do a select index character, and then we'll say word. Okay. And then we're going to do a inner join by characters. Cool. And then we're going to do we're going to use another inner join. And this is how you do a basic sentiment analysis using TidyText. Say inner join get sentiments lexicon equals, and we'll say Bing. Okay. Bing. So what this is doing is basically a lexicon is a dictionary that's been kind of labeled as what are we saying are positive words, what we're saying are negative words. So when we see, so in the Bing lexicon believes the word good is a positive word. The word right, well, like are positive words. The word sorry is a negative word. Okay. And now we're going to actually just kind of um, and when it joins it together, it's saying like it has a word and its sentiment, and if it finds that word, then it'll just pair it up with this sentiment, and it'll just remove anything that doesn't have any sentiment. Cool. Okay. So now what we're gonna do is we're gonna do a group by index and character, and we're gonna do count sentiment. So now for every episode, for each character, we're counting the sentiment for each episode, the total sentiment for all the dialogue. Okay. We're going to ungroup that, and we're going to ggplot AES x equals, I want to say x equals index, y equals n, color equals, actually we'll say y equals n, color equals character, plus geom point, plus geom, yeah, we'll just geom point, plus facet wrap, and we'll say sentiment. So what this is going to hopefully do is it's going to create two plots where each character will have its own points representing color of the positive and negative sentiment trends. And I'm just doing GM point first just to make sure everything looks right. Okay. So what are we seeing here? This is pretty much a mess, right? I'm curious. Maybe it isn't the best to do by character. Maybe we should do it by season. So we're gonna select by season. Okay. And then we'll just do group by season and index. And okay, I got a better idea. We'll just do first this. Okay, and then we'll ggplot AES x equals season. And I got an idea. We'll do we'll mutate. We'll do a mutate episode. We'll say episode index equals paste index and season. Sep. Oops. Maybe. Actually, no. I think it'll be fine. We'll say ggplot AES x equals index, y equals n, color equals season, plus geom point plus facet wrap, and we'll say sentiment scales equals free. Let's see what that looks like. Okay. So our positive and negative sentiment looks pretty same. Actually, I'm going to do scales equals fixed so we can do an easier comparison. And I'm going to do a GM smooth s equals false. And then let's see here, group equals sentiment. Hopefully this will show me some type of pretty flat. So smoothing doesn't really do a lot. There's kind of it's kind of a nightmare for it. Interesting. Here's one thing that I think that would be a little bit easier to understand. We'll just do we'll do a geom box plot, and instead of, we'll say, boom, season. What is going on here? Yes, x equals season, y equals n. What? Why is it not showing here? Just that. Let's see what's going on here. Okay, ggplot, and then we'll do ggplot as. Oh yeah, we'll just actually, yeah, we'll just do sentiment per season. This seems like an easier way to do this. So we'll do select season, group by season, count, sentiment, ungroup, boom. And then we can do ggplot as x equals season, y equals n, color equals sentiment, geom point plus geom smooth. Okay. And then we'll say group equals sentiment. See, right here is a much, this is the thing there where I was really kind of overthinking it and thinking that I should do a very specific, very detailed chart, when in reality we can see this overall sentiment right here, right? But a problem with this chart is that sentiment is just on frequency of words. So some seasons might have more words that have just been said, right? So what we're gonna have to do is we're gonna have to do some type of standardization, right? So we might have to do sentiment per word, and that'll be pretty easy. We can just do that pretty quickly. So we're gonna do that. We're gonna select, and then we're gonna say count season, add count per season, and then and then we're gonna do a we're gonna rename that to and as was it season count. What was add count at the add count season, and then we'll say name equals season word count, right? Okay, and then we'll say inner join get sentiment lexicon equals Bing, and then we'll say group by season count word, count sentiment, and we'll say add count sentiment, ungroup, select season, and we'll say we'll do just a mutate n equals, actually we'll say sentiment score equals n divided by season word count. Right, and then we'll say select season sentiment and sentiment score unique. Why? Oh, I spelled season wrong. Right, and then we'll do a ggplot AES x equals season, y equals sentiment score, color equals sentiment, geom point plus geom smooth, SE equals false. And you know what? I bet we're gonna have to do a group equals sentiment too, just to make sure ggplot isn't confused. And I'll make sure to, this time I'll do fig.height equals 15, fig.width equals 15. Oh, and then I have to do a comma. Okay. Why is my plot doing this? There we go. And we can see that it's still the same thing. This thing is way too large, so I'll do 10. Right, and we can see that overall, honestly, it still is playing the same picture where positive sentiment is much higher than negative sentiment. However, it stays pretty stagnant, right? I would say maybe positive sentiment has decreased a little bit, but it's still not enough where I would say that it's a big deal. Cool. Okay. So what else should we be doing? Let's see here. Let's create let's analyze 3 characters, 3 of the main characters. Okay, so we're gonna do word df, and we're gonna select the index, character, and word, and we're gonna filter character to be either Michael, Dwight, and Jim. Okay, and I'm just gonna make sure that we selected the right characters. Michael, Dwight, Jim. Okay. And what we're gonna do is we're gonna do a different lexicon. We're gonna do get sentiment lexicon equals, and we're gonna use the NRC lexicon instead. Oops, and I totally get sentiments. Oh, I could wrap an inner join. Inner join get sentiments. Right. And we're gonna do a first of all a group by character index, add count, word name equals word. We're just gonna call it a word count just to not confuse it. Word count. And then we're also gonna count sentiment. Oh, we're gonna add another count and say sentiment. Okay, so now we have the sentiment for that episode. Okay. Okay, NRC get. Let's see. I'm just making sure that all the sentiment makes sense. Cool. Okay. Okay, and we're gonna select index, character, sentiment. Actually, we're gonna do a mutate first, and we'll say mutate sentiment score equals n divided by word count. Okay. Select index character sentiment score. Okay. ggplot AES x equals index, y equals sentiment score, color equals sentiment, geom point plus geom smooth, s equals, we'll say s equals false for now, plus facet wrap because we want to view all the characters first. Character, and we'll say scales. Oops, scales. Yes, oops, scales equals fixed. So now we're trying to look at basically a time series of sentiment for each character. And this is through their dialogue. So like, oh, is Jim saying more positive stuff throughout the season, or is he just kind of staying consistent? Is Michael saying happier stuff, or is he saying more angry stuff? Oh, okay, just that. I gotta do one more thing. And then we'll say group equals interaction, character, and sentiment. And that group equals, okay, let's see if this actually works first, but let's see here. It's taking a while. Okay. The fig dot width equals 10, fig dot height equals 10. Okay. So we couldn't do a crazy interaction. That's pretty interesting. Okay. You know what? We might have to add another sentiment. I'm gonna actually do another facet. So I want to do character for each individual sentiment. Actually, no, I'm gonna do something else. I'm gonna do if you see right here, it's a mess. There's way too many sentiment scores. So I'm gonna do it for each sentiment. The color will be the character, and then their interaction will be character and sentiment. Hopefully, this will fix everything so it makes it look fine. Okay, let's see what's going on here. Interesting. Well, we can see that Michael was saying a lot of anticipation words or words that were ranked really high. If we see just overall, Michael has the highest sentiment in general. If we see on the upper plane areas, you always see blue, right? So I'm gonna actually do another transformation. So I'll do scale y log 10. Okay. And after this, we'll go on to another thing because I'm sure you guys are tired of looking at these sentiment scores. Okay, so it's kind of is a mess. I really, man. Oh well, we'll be fine with this. But actually, I think I should. I want to do one more thing. I think I'm gonna do it instead of index. I'll do it by episode. Episode, and we'll do episode. Episode. Okay. Oops. Episode. All right, one more time, and then we'll call it. I don't know if this will change anything. What is it? Can subsect index. Oops. Episode. While it's doing this, we're gonna move on to another thing. Finally, what I want to analyze is let's figure out what are the catchphrases. So, what are the distinguishing catchphrases for each character? And when I say distinguishing for each character, that should just right now pop up TF-IDF. So, we're going to select character and text. And then we're going to do the unnest tokens. Okay, there we go. Interesting. Again, so now it did make it a little bit easier, better. Technically, the index, when I did it by episode, I should have done episode index instead. But we can see that overall, Michael has higher sentiment in general. Cool. Okay. I'm kind of over this now. So we're gonna select character text. We're gonna do the inner join by characters. And now what we're gonna do is we're gonna use bind TF-IDF, and this time instead of not bind TF-IDF, we'll do get unnest tokens. Unnest tokens. And our output will be ngrams. Since we're going to do an ngram analysis, our input is text, our token equals ngrams, our n, we're going to say our n equals 4, right? We'll do 4. Actually, no, we'll do, I'll do multiple ones. So we'll do 3, and we'll just say trigram 3. Actually, yeah, trigram df, and then we'll say count character ngrams. So we'll say we'll call this a trigram because it's pairing of 3 words, and then we'll call this a quadgram, which will be a pairing of 4 words. So 4, and then we'll do a quad. What is it? A quant? I think it's quantgram. So we'll just call it a quantgram. And we'll call this 5. Oops. Okay. So this is still running for some reason. We'll run that. And you know what? I've already decided I'm not going to do 5 gram. That's a little excessive. So with our trigram, since we already have our trigram, we'll do a TF bind TF-IDF, and we'll say it's our ngrams character, and n. We'll say group by character, and we'll say top n TF-IDF n equals 3. Ungroup Boom. We'll do the same thing for the quadgram. Okay, let's see what's still running. Okay, there we go. Okay, and we'll call this trigram again. Trigram. Okay, and quadgram will be the same thing right there. Okay, and then we'll assign our quadgram too. And finally, we'll do a mutate. So mutate. Actually, no, we'll just we'll just plot it out. So ggplot ASX equals reorder within Ngrams TF-IDF, and we'll say character, and then we'll say y equals TF-IDF, and then we'll say fill equals character plus geom column plus scale x reordered. Scale x reordered plus facet wrap character scales equals free. And actually, I'm going to do a core flip too. Boom. Trigram. Trigram. So what we're doing right now is finding the groupings of three word groupings, and doing a TF-IDF. So we're finding what 3-word groupings distinguish each character, and we're finding the top 3 word groupings. Okay. What's going on here? Okay. I got it. Fig dot height equals 15. Fig dot width equals 15. And there we have it, right? Nardog is the most distinguishable word for Andy. Pum Pum and the senator. Na na na. So that's when he was singing that song. Dwight Schrute is Dwight Schrute. Jan's Michael. Jim's is Owimbawe. Let's see here. Kevin's is warning for some reason. Pam is this is Pam. Okay. What I'm curious is, let's look. So these are the distinguishable like catchphrases, I guess, for those characters. But I want to look at instead of trigrams, I want to look at the quadgrams. So I'm going to look at the quadgram first, and the quadgram might run into some issues. I want to first look at just see how many rows there are. So 173. Here's how to find it, like kind of like do a quick and dirty way to filter it. So we'll say a group by character, arrange by descending TF-IDF, slice 1 through 3. Group. Oh, oops. Why am I group by slice 1 through 3? So that way it's saying like, okay, we're taking the top 3 TF-IDF scores. Even if there's a tie, we're just going to select whatever is the first 3. Okay. And that's basically how you like resolve ties really fast, or how I do it really fast. But you can also specify in like top N on its how it resolves ties. But I really don't know how to do that. So we're going to do this, and then we're going to apply this function. And boom. Oop, and I totally dot fig dot height equals 15, fig dot width equals 15. Gotta restart it. I'm not sure why I mean, this laptop's pretty bad, so it's gonna be a slow. Um, it renders it pretty slowly, but okay. Bum bum bum, la la la, blah blah blah. I'm gonna do that. I'm gonna a couple of bucks. So what's funny about Daryl is it's the na 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 song. For Dwight, his most iconic thing is this is Dwight Schrute, where he's answering the phone. Again, Aaron Dunder Mifflin. This is Aaron, and he's coming back today. Interesting. Let's see here. Again with Jim, it's a Wimba, the Lion King song. That's pretty cool. Okay, I want you to beep beep beep. Let's see what else. Again, with Pam Dunder Mifflin, this is Pam. Was when she was a receptionist. Nope, nope, nope. That's funny. You lost your mind. Have you lost your mind? Okay. So we found is catchphrases for each character. Each character. Top 3 catchphrases. Okay. Well, I hope this helped everyone kind of just get their dip their toes into text mining. This is really kind of how I do a preliminary basic EDA whenever I view text, and it's actually very useful. And what's really cool about text mining is that um, it's very new. So all these techniques are still being developed, and sometimes text mining is both an art and a science where you really do need some domain knowledge to understand what is saying here, who's the user, um, who's saying this text, what are they actually meaning for, what are they meaning to say, and also how sometimes a simple just count of words can really get you pretty far. So yeah, hopefully this helped everyone. I'll see you next week, and yeah, tidy on. Stop sharing.